I'm Rory.
And I'm Ricky.
And today we're going to be talking about the minimum spanning tree, which is an algorithm that we can use to solve some graph-based problems in coding. Specifically, we're going to be talking about Kruskals' algorithm for minimum spanning tree. So let's get started. First, let's explain the concept in words. Minimum spanning tree is an algorithm to determine the minimum weight needed to fully connect a network with potential weighted edges. It essentially selects the edges that will allow for the minimum weight out of an edge pool.
Right?
Yeah?
This doesn't make any sense.
It's all right, Ricky. Let me explain with an example. Let's say that we have 5 cities and we need to build bridges between these 5 cities, but each bridge costs a different amount. So we want to know how we can fully connect these cities with the least amount of money. Fully connected meaning that we can visit any city from another city. Now does it make sense?
I know what the problem is now.
Right, so now let's take a look at the solution. We use disjoint set union, which means that we make every city a node in a graph, and then we define a struct with parent and value. Initially, we make each node its own parents, but as we select bridges, we change the parent. For example, if A and B are being connected, then we make A the parent of B. Additionally, while choosing bridges, we want to have a total variable that tracks the total cost, meaning that as we place bridges, we add the cost to the total cost variable.
Right?
Yeah?
So when you say change the parent, does that mean change it to the direct parent or the root of the entire graph?
Ricky, that is a great question. Now, I'd like to make this a note for everyone. When you are changing the parent of a node, change it to the root of the entire graph, not the direct parent.
Why is this so important, Rory?
Well, this is extremely important because it will help us tell if nodes are actually connected. For example, let's say we want to see if nodes C and D are connected, but C's parent is A and D's parent is B, so we say they aren't connected. However, let's say B's parent was actually A. That means that they are connected because their root parent is A. But because we only made the direct parent of B, we thought they weren't connected. Does that make sense, Ricky?
Yeah, it does.
Great. Let's continue. So now that we've talked about what to do after we choose the bridges, let's see what happens how we select the bridges. Now, the order of the bridges we select depends on which algorithm we use. And today, we'll be talking about Kruskals' algorithm for minimum spanning tree.
Rory, you use such weird terms. What does Kruskals' algorithm mean?
Oh, Ricky, you're so impatient. I'm getting to it. Kruskals' algorithm is an algorithm where we sort the edges by weight. Then we run through the edges from least weight to most weight using a for loop. If the 2 nodes the edge connects are already connected, then we skip the edge. But if they aren't, then we add the edge to the total cost variable and change the parent.
Great! So this makes sense theoretically. Now, can you give me an example?
Sure, Ricky. Let's take a look at an example that I gave previously, but now we've sorted these 8 edges. First, we start with the edge of AB, which has a cost of 2. We see that A's parent is A, B's parent is B, so they aren't connected and we can lay down this edge. Then we take a look at AC. We see that A's parent is A and C's parent is C, so again, they are not connected and therefore we can connect them. Similarly, C's parent is A and E's parent is E, so again, we can connect this edge. But now, let's take a look at the edge of AE. A's parent is A, but E's parent is also A, meaning that this edge does not need to be laid because A and E have already been connected. Next, let's take a look at the edge of ED. We see that E's parent is A, but D's parent is still D, so we can again lay the edge. Now that we can see that all 5 of the cities are connected, that means that all the edges that we use now will be redundant, meaning that AB, AC, CE, and ED is our solution for the minimum spanning tree. As you can see, Ricky, we've used the Kruskals algorithm in order to solve this problem to find the minimum cost we need to connect these cities. Got any questions left for me, Ricky?
Oh, just one more question.
Go on.